We spend so much of our time and energy trying to make our computer chips absolutely perfect, silent, predictable, clean. We're always fighting against things like heat and timing errors and electrical fluctuations. We just call it all noise, and we try to get rid of it. But what if we've been looking at this completely backwards? What if that physical chaos, the very thing we've been trying so hard to suppress, is actually a kind of hidden language? A powerful computational resource just waiting to be tapped into. Well, a fascinating new paper suggests that this noise, it isn't just a nuisance. It could literally change the way we think about computing. So, to really wrap our heads around this, we need to step into the world of neuromorphic computing. This is a field that's all about building computers that don't just run brain-like software, but are actually built on brain-like hardware. Now, what's so cool about this is that these chips work in the analog world, a lot like our own neurons do. So instead of these rigid, perfect ones and zeros, they use the continuous, kind of messy physics of the silicon itself. And the payoff for this is potentially incredible energy efficiency. We're talking millions of times less energy than a normal digital chip needs to do the same job. It's a huge deal. But there's always been a catch, a big one. These little analog brains, as brilliant as they are, have always needed a digital babysitter, a regular computer to feed them data and to read what comes out. And this creates this really clunky, slow, inefficient translation layer. Imagine trying to have a deep, fast conversation through a really slow translator. You lose all the speed, all the nuance, it's a bottleneck. So a group of researchers decided to try something pretty radical. They thought, what if we stop translating? What if we could just get two analog systems to talk to each other directly in their own native physical language? And their setup was just ingenious. On one side, you've got a standard AMD graphics card, a GPU, but they weren't using it for graphics. Instead, they were just listening to its raw physical hum, its voltage fluctuations, its thermal changes. And on the other side, they had a special reprogrammable chip, an FPGA, running 128 simulated neurons. Then they just built a bridge between them and let the GPU's physical noise whisper directly to the artificial brain. But here's the key. Not all noise is just random static. The researchers were hunting for a very specific kind of signal. It's something you find everywhere in nature, from the rhythm of your heartbeat to the ebb and flow of traffic. It's called 1F noise. Okay, so think about it like this. Useless, random white noise is like TV static. It's totally patternless, just chaos. But 1F noise, that's like the jagged shape of a coastline or a piece of music. It has structure, it has complexity, and crucially, it has a memory of what came before. It's not just random, it's organized chaos, and that organization is absolutely packed with information. And this is exactly what they found. I mean, look at this graph. When they measured the physical signals coming right off the GPU, they saw this classic steep slope of 1F noise. That flat line, that's boring old white noise. The steep lines, that's the GPU. It wasn't just producing meaningless static. It was naturally creating this complex, structured, and as it turns out, incredibly useful signal. So, let's get to the results, because this is where things get really interesting. When they piped this special 1F noise into their artificial brain, it didn't just add randomness. It actually added order. To get why, you need to understand this idea of criticality. A system is critical when it's perfectly balanced, right on the edge between being too rigid and predictable on one side and too random and chaotic on the other. The best analogy is a sand pile. You keep adding one grain of sand at a time. Nothing happens. Nothing happens. And then one more grain causes a huge avalanche. That state, right on the edge of chaos, is the computational sweet spot. It's where systems like our brains do their best work. And would you look at this? The data is just stunning. The blue bar, that's the GPU's 1F noise. It pushed the artificial neurons to a state of almost perfect criticality. Now look at the yellow bar. That's what happened with random white noise. It just shoved the system into a useless, chaotic state. The GPU's natural, structured noise was like a conductor, guiding this whole orchestra of neurons into perfect computational harmony. And how much better was it? 27 times. The GPU's natural noise drove the system 27 times closer to that perfect computational state than random noise did. This wasn't some tiny little effect. This was a massive, fundamental shift, all because they decided to embrace the noise. So this alone was a huge breakthrough. But as the researchers kept digging, they started to realize something. The story wasn't just that the GPU was a good noise source for another computer. The truth was way, way bigger than that. It turns out they didn't need the second chip at all. The GPU wasn't just a noisy neighbor. It could be the entire neuromorphic computer, all by itself. By reimagining the GPU's own internal physics as computational parts, they actually built a virtual computer right inside the GPU. And the results were just mind-blowing. On a key test, this GPU-only brain scored 100% accuracy, beating out standard models. The noise wasn't just a helpful signal anymore. The physical things creating the noise, those were the neurons. So what are these secret neurons? Well, they're not code. They are actual physical events happening on the chip. Things that chip designers usually see as problems, like L1 bank conflicts. That's basically creating an intentional traffic jam in the chip's memory to generate a useful signal. Or branch divergence, which is like when a group of calculations has to split up, creating a timing difference that acts like a switch. Every one of these 7 behaviors became a reliable, deterministic tool for computation. But they found a really fundamental trade-off. Some of these physical effects, like those memory traffic jams, turned out to be amazing at performing complex logic, but they completely wiped out any memory of what happened before. And others, like that herd splitting, were fantastic for remembering things, but were pretty weak when it came to complex logic. You couldn't get both from the same physical trick. So what was the solution? It was brilliant. They just copied the biological brain. They created different specialized groups of these virtual neurons inside the same GPU. So one group would handle memory, another would handle the complex logic, and so on. And you can see it right here in the table. The specialized 4-pop design just blew the unified approach out of the water, solving that trade-off and getting amazing performance across the board. Okay, so this is all incredibly cool, but what does it all mean? What are the big picture implications? Why does this matter for the future of how we compute? Well, it boils down to a few huge ideas. First, that line we've always drawn between hardware and software, it's starting to completely dissolve. The physical reality of the silicon is becoming part of the program itself. Second, it proves that what we've been calling noise is actually a rich, powerful physical process we can put to work. And this really points to a future of hybrid computers, where perfect digital logic works together with the messy but incredibly powerful physics of analog systems. We're talking about a new generation of machines with just unbelievable power and efficiency. And you don't have to take my word for it. The researchers themselves said it best. That boundary we've always created between the digital controller and the analog device, it's artificial. We made it up. And this research proves we can start to erase it. So it leaves you with this one really fascinating question. If a standard off-the-shelf GPU has a secret analog brain hiding inside it, what other powerful, secret computational languages are just lying there, dormant, in the physics of the technology we use every single day, just waiting for us to discover them?